My dear students, welcome to this session number 16 of Industrial Metallurgy. These are the contents that we'll cover. Okay, so if you remember 2 sessions before, we had started our discussion on binary phase diagrams. But then since binary phase diagrams are drawn for binary alloys, we went on to see as to what is meant by an alloy system. And then we went on to see that what are the different types of phases which exist in an alloy system. And then in the last session, we also tried to understand as to how is the solidification of an alloy system different from that of a pure metal. Okay, so let's get back to the binary phase diagrams. And in this binary, we had started our discussion with classification of phase diagrams. And in classification of phase diagrams, we had said that equilibrium diagrams are classified on the basis of the number of components present in a material system for which the equilibrium diagram is being drawn. So whensoever an equilibrium diagram is drawn for a one component system, a pure substance, a unary system, the equilibrium diagram for all such systems is called a unary equilibrium diagram. Similarly, if an equilibrium diagram is drawn for a two component system, in other words, if an equilibrium diagram is being drawn for a binary alloy, all such diagrams are called binary phase diagrams. So in two component systems, in binary alloys, composition is also a variable along with temperature and pressure. So if we have to show the graphical representation of what different phases are present in the binary alloy, we have to show this with taking composition, temperature, and pressure as the variables. But fortunately, as I said in earlier sessions also, in most of the binary alloys processing, the pressure is kept fixed at 1 atmospheric pressure condition. So there are only two variables, and so binary equilibrium diagram is a graphical representation of what different phases would be seen in a binary alloy under different conditions of temperature and composition. So when we draw this binary equilibrium diagram, temperature is taken along the y-axis and composition is taken along the x-axis, and then the diagram shows that under different conditions of temperature and composition, what are the different phases and their details which are existing in a binary alloy. But then even under binary equilibrium diagrams, we have done some classification for binary alloys. Means under binary alloys also there is categories of binary alloys, and this categorization has been done number one on the basis of the relative liquid solubility and the solid solubility of the two constituent elements. And this classification is also done on the basis of certain reactions which the two constituent elements show against each other. But in our syllabus, we only have classification of binary alloys on the basis of the relative liquid and solid solubility of the two constituent elements. And on this basis, the binary alloys are of three main types. Type 1 binary alloys, which are also called isomorphous binary systems, or extended or extensive solid solution alloy systems. Then we have type 2 binary alloys, which are also referred to as eutectic systems. And the last category is type 3 binary alloys, which are also eutectic systems. Now type 2 and type 3 are both eutectic systems, but there are some points of difference between the two, which we'll discuss when we take up these systems in more detail. So students, now what are type 1 binary alloys? As I said on the last slide, the first category of binary alloys on the basis of the relative liquid and solid solubilities of the constituent elements is type 1, type 2, type 3. So let's in this session discuss about type 1 binary alloys. Binary alloys in which the constituent elements show 100% liquid solubility as well as 100% solid solubility are called type 1 binary alloys. Now what does that mean? When I say complete liquid solubility or 100% liquid solubility, it means that for the binary alloy, you take the two constituent elements in any weight ratio. In any weight ratio in which you take them, they'll always show liquid solubility, they'll always form a solution, they'll always show one phase when they are in the liquid, and that phase would be a liquid solution of the two constituent elements. And what does complete solid solubility means? Complete solid solubility means that when you take these two elements, you can take them in any weight proportion, and when the system on cooling gets solidified, these two constituent elements will always form a single solid solution irrespective of their weight proportion. So for example, if you take two elements A and B to form a binary alloy, if they are showing 100% liquid solubility, that means you take 1% A, 99% B, or you take 1% B and 99% A, or you take any weight ratio. When these two constituent elements are in the liquid state mixed with each other, they'll always form a liquid solution, single phase. And when these two would solidify, 100% solid solubility means you take them in any weight ratio what you can think of, they will always form one solid solution. Means when you look into the material system, which is a type 1 system, which is showing 100% liquid solubility and 100% solid solubility, when the system is in a completely liquid state, it has got one phase in it, liquid solution. When the system is in a completely solid state, it has got one phase in it, that is solid solution. Okay. And in material science course, you must have learnt about the Hume-Rothery conditions for the formation of substitutional solid solutions. Students, very briefly, I'll tell you about these conditions. Hume-Rothery, which was a great scientist in the field of material science and metallurgy, he had stated that if two elements have to form a simple substitutional solid solution, simple means not necessarily with 100% solid solubility. So he said that they have to obey four conditions. The first condition is of their crystal structure. Their crystal structures must not be very different. Atomic size. He had said that the two elements' atomic sizes must not be very, very different, must not be more than 15%. Then chemical affinity. In the third rule, Hume-Rothery had said that if two elements have to form a simple solid solution, they must not have great chemical affinity. Means if one of them is electropositive, the other must not be very electronegative, so that they tend to form a compound. And the fourth rule, he had stated that when you are trying to form a binary alloy out of two elements, the element which has got higher valency must be taken as the solute and the other as the solvent. It always forms a better commercially useful alloy. Now, if you want to see these rules, that what are the rules for type 1 systems, the first rule, that is crystal structure rule. See, for simple substitutional solid solutions, Hume-Rothery had said that their crystal structure should not be very different. Means if one has a simple BCC crystal structure, the other should not have a very complicated orthorhombic or some other type of, both should have simple crystal structure. It can be BCC, FCC, or FCC and HCP, or HCP and simple cubic, right? But if it has to be a type 1 binary alloy where 100% liquid and solid solubility has to be shown, Hume-Rothery said that there is a modification. Two elements can show such wonderful solubility only if they have the same crystal structure. No exceptions to this. Then atomic size. In the second rule, Hume-Rothery had said that if two elements wish to form a simple solid solution between them, their atomic sizes of the two elements must not be greater than 15%. Here again, he made a modification, and here Hume-Rothery said that if two elements have to show 100% liquid solubility and 100% solid solubility, then their atomic sizes difference must be less than 8%. And if these two conditions are met, the third and the fourth condition automatically get met, and you are able to form a type 1 system. And as I said in the last slide, these systems are also called extended or extensive solid solutions. The reason is that if you keep on varying the composition, the weight proportion of the constituent elements, for each specific weight proportion that you will take, a specific solid solution will get formed. So for a range of compositions of the two constituent elements which can form type 1 system, you will be able to form a series of solid solutions. And for that reason, such systems are called extended or extensive solid solution alloy systems. Also, in the last slide, we said that these systems are called isomorphous systems. You see, I said that if two elements have to form a type 1 system, their crystal structure must be the same. So both the solute as well as the solvent elements must have the same crystal structure. And when they are combined and they form a solid solution always has the crystal structure of the solvent. So solvent, solute, and their solid solution will have the same crystal structure. Iso means same, morphous means structure. So because when type 1 systems get formed, the solute, the solvent, as well as the final solid solution that gets formed have got the same isomorphous structure. They get this name, isomorphous alloy systems. Now, to explain this type 1 system, there are only a few pair of elements which can actually act as type 1 systems. Copper, nickel is the most common example. Gold, silver is another example. Gold, platinum is another example. Platinum, silver is another example. So all these NRI type of metals form type 1 systems with them. Now you see copper and nickel have nearly same atomic size for their atoms. They have the same crystal structure FCC, and they form a series of solid solutions, and they form type 1 systems. Thanks for watching. We'll now go into the details of the construction of equilibrium diagrams for type 1 systems, and that I'll discuss with you in the next session. Hope you enjoyed this session. Thanks for your time and thanks for watching.